You will see the time it takes for the light to go back and forth. And in fact, laser ranging is used every day by geometers, people who, for example, if you want to measure the size of this room, there is a laser pointer that you send, and you look on your meter, and it tells you it's 12 meters to this wall, it's 6 meters to this wall. How does it work? It's just looking at the time it takes for a light beam to be reflected from the wall. But at that time, very long ago, there were no laser did not exist, and there was no way to do that. The first precise measurement was made in the 19th century with spinning wheels. You send the light through a wheel which is spinning very fast, so when the light goes through the hole, it makes a pulse of light going to a mirror, and when it comes back, the wheel has turned, and so it's blocked. And you have to adjust the velocity of the wheel so that the beam will go out and come back when the next hole is coming in front. And from then, the velocity of light was measured. But this is not calculated. The first guy who was able to calculate the speed of light was Maxwell. When he wrote his Maxwell's equation, there was one equation which gave the velocity of the wave that he had in this equation. And he found that this velocity was precisely equal to the velocity measured by the experimenters. And so he concluded that light was an electromagnetic wave. But before Maxwell, it was not, nobody thought that light was something related to magnets and to electrical currents. So this was really a breakthrough. And the velocity of light now is known with such a precision that physicists have stopped trying to measure it more precisely. It makes no sense, because to measure more precisely, you need to have a meter definition more precise. And there is the definition of the meter was less precise than the measurement of the velocity of light. So physicists have turned things around and have decided that the velocity of light was fixed, and the meter was defined as the time it takes for the light to travel during a given amount of time. So now the meter is defined as a fraction of a second, corresponding to the length, the distance over which the light is traveling during this fraction of a second. And so this has allowed physicists to replace two units, time and length, by only one, provided that the velocity of light is fixed to a given value.
Yeah, this question pertains to the universe. If really life exists elsewhere other than Earth, yeah, why they have not contacted us or come to us themselves yet?
So, first of all, why would they want to contact us? But I think this is a very interesting question. It's related to the search of exoplanets, and this is also, I come back to the first question which was asked, what are the interesting fields which are open now for research? One of them is certainly in astronomy, the search for extra light outside the solar system. 20 years ago, the astronomers had been able for the first time to not only to look at stars, but to look at planets. And this is a fantastic achievement in terms of instrumental physics, experimental work, because the planets are very, very light compared to the stars and very small compared to the stars. And you need a huge sensitivity to be able to observe, to have an evidence for planets. The first evidence is given by the fact that if a planet is rotating around a star, it slightly modifies the motion of the star itself. It perturbs the motion of the star, and now the star is the star plus planet system which rotates, and so it wobbles a little bit the motion of the star. And this wobbling motion can be detected, because if you look at the light coming from the star, when the star is going towards you, the light is shifted in frequency by the Doppler effect in one way, and when it goes away, it is shifted the other way. So by looking at the modulation of the Doppler effect of stars, one had the indirect evidence that something was rotating around the star. But this was indirect. And then one made more direct measurement. If the planet is going in front of the star, it will make a partial eclipse of the star. You know, when the moon is going in front of the sun, it's a solar eclipse. But the moon is very big in the sky; it covers the sun completely. But when a planet is going in front of a star, it covers only a very small fraction of the star surface, so it just dims a little bit the light of the star by 1 part in 1,000 something less. So with very precise instruments, one is able to see how the level of light from the star is going a little bit down and up, and from that you can also find that there are planets. But then you have to decide, is this planet able to sustain life or not? And for the planet to be able to sustain life, it needs to be not too close to the star, because then the temperature is too high, nor too far, then there is no way, there is not enough energy and light. So it has to be in the right distance range. Moreover, it has to be a planet like the Earth, a rock planet, not a gaseous planet like Jupiter. So now thousands of exoplanets have been found, and they are sorted out, classified according to which one is a good candidate to support life. Then you have to decide whether the conditions for life exist. That is, you have to measure the atmosphere of the planet, and for that you have to do spectroscopy. You have to take the light from the planet, analyze its frequencies to find out whether the elements required for life are there or not. We are not there yet because the sensitivity of the instrument is not high enough to do this kind of measurement. But this will come. And there are so many planets. I think there are something like 10 to the 11 galaxies in the universe, and each galaxy has about 10 to the 11 stars around it. And all stars have planets, so certainly there are millions of planets on which the conditions for life are realized. So it's very likely that there are various forms of life, but are they the same one as we have here? We don't know. And why did they not communicate with us? There is a very simple explanation. The closest star from us is 4-year light. That is, it takes 4 years for the light to go from the closest planet to us. And most of the exoplanets we have seen are hundreds of thousands light years from us. So it will take a huge amount of time for the light to come to us. And more, so maybe some of these planets have developed civilization long ago, but how we will be able to understand signals that are, what kind of signals should we send? In which language? Should it be English or French or Hindi? I don't know. And what kind of signal should you send? I think the NASA has tried, when they sent the first Pioneer probes outside the solar system, they put in a box a small message. And I think what they sent out is, first of all, you have to find what kind of, if you send a message, a mathematical message is maybe the most universal one. So maybe you should write a number, for example, pi or e, one fundamental, a dimensionless number, or the fine structure constant, which is a dimensionless number. But then you have to decide in which unit. So the simplest one is to take a binary system. Put a sequence of 0 and 1, which make up either pi or the fine structure constant, or any fundamental dimensionless quantity. So this has been done, and I guess an outer civilization should do that, but when you receive the signal, the civilization might be gone for thousands of years already, because it takes such a long time. And there is another issue here, is that I don't think it will ever be possible to go there, because it will take thousands of light years, and we will never travel at this velocity, so it will take millions of years just to get there. So it's completely out of question. So it's why I think this is really the ultimate definition of blue sky research. We don't do that because we will colonize these places. We don't do that to protect ourselves against colonization from them. We do that only because we are curious. We want to know if life exists there and how it can be sustained there. And we have only evidence of things that we cannot reach. And I think that's the best, the most beautiful example of blue sky research.
Right? What made you think that you should start a research on photon?
Okay, I tried to explain that on the first day. It's a question of circumstances and luck and chance. What I was interested in at the beginning is just mathematics and physics, and the fact that mathematics and physics were related to the fact that you could use mathematics to explain simple physical laws. But at that time, when I started, I knew only the laws of mechanics, Newton laws, and when I started going into the high-level education institution where I went, which is École Normale, it turns out that I was lucky to have lectures by people doing atomic physics and optics, people who were working on the interaction of light with atoms. And I found their lectures very clear and fascinating, and I just went into this direction because I had good teachers in this field. And as I said, it was also the time when the laser started to be developed, and it was also clear that this was a fantastic tool to investigate deeper. So it's not only important to understand what other people have done, but it's also very important to have a tool which will allow you to go further. Not because you are more bright than these other people, just because you have this opportunity coming from this new instrument. So I started working on that with my teachers in Paris. And then when I got my PhD, I decided I had to get another experience, and I went to the United States, in Stanford, working with Art Shallow, who was an American physicist, who was working with lasers. In Paris, I did not work with lasers. I knew the lasers were being developed, but we did not have the kind of lasers which would allow us to do the experiments. What we needed are very lasers called tunable lasers, lasers whose frequency can be changed so that you can hit the lines of various transitions in atoms, and you can use this light to selectively excite one state or another one. These lasers did not exist when I started, and they started to be developed by companies in California, near Stanford. It was going to become Silicon Valley later, but it was already very active in this field. So I went there, and I worked with Art Shallow for 1 year and got used to these lasers and brought them back to Paris. And then I had a fantastic instrument, fantastic device to start to explore things which could not be explored before. So it came naturally. But I have other colleagues, other friends who were working at that time, who went into condensed matter physics instead of atomic physics. And they did very important things because condensed matter physics also had a tremendous development with superconductors, study of superconductors, semiconductors, and all very fascinating topics also. So I did not choose the topic. I must say that it is a topic which chose me because I felt at the right time in the right place.
Okay.
Okay, so the question is how can the photon have energy if it has no mass? That's because the photon is a quantum particle. The relationship between mass and energy, kinetic energy in classical physics, it is E equal mv squared over 2. But in quantum, in relativity, the formula, in quantum in relativity, formula is E equal mc squared. So again, it seems that you need mass. But in fact, E mc squared, this is the energy, the rest energy of a mass. But if you take the more general formula, which is for a particle which has mass and velocity, you find that the real formula is E equal to square root of m squared c squared plus p squared c to the fourth, where p is the momentum. So you see that the real formula has a part which does not depend on mass, but only on momentum. For the photon, if the mass is 0, the solution of this is E equal pc. And you see that the photon has energy and momentum without mass. So it's not in contradiction, it's just the fact that you have to use relativistic equations in the case of the photon. The photon is a quantum particle with no mass, and nevertheless it carries energy proportional to its frequency. It is, okay, it's a conclusion of relativity theory. it's clear that you cannot go faster than light because it would require, when you approach the velocity of light, the energy which is required to go at this velocity becomes higher and higher. The mass of the particle becomes bigger and bigger, and so the velocity of light is a limit which cannot be crossed. And it's also the fastest way of transmitting information. You cannot transmit information faster than light because this would violate causality. At some point, you may have the feeling that quantum physics might violate causality because of a process, a phenomenon called entanglement. The fact that if two particles have interacted and you separate them by a very large distance, what you do on one particle has an immediate effect on the probability of finding results on the other. But this kind of correlation cannot be used to transmit information, and there is no way to transmit a signal at the velocity faster than light. So I would say it's not an assumption, it's a consequence of the equation of relativity, which have been checked many, many times. So maybe, it relies on a theory. And of course, all theories are subject to verification by experiments. So you might think that one day you will find that theory of relativity or gravitation is not complete, has to be modified. But up to now, nothing indicates that. And moreover, even if it is going to be modified, it means that it does not mean that all what has comes from in this theory is wrong. For instance, Newton has been modified by the theory of gravitation, but Newton is not wrong. In the limit where you apply Newton's equation for motions which are not too fast, not too close to the velocity of light, Newton's law are very good approximation. So relativity and quantum mechanics will hold for a lot of phenomena, and there is no indication that the principles of relativity and the principle of quantum mechanics are wrong.
Yes, sir. So one more question on the universe, that does parallel universe really exist?
Does what?
Does parallel universe?
Parallel universe? By you? I don't know. So again, there are two aspects to that question. There are some people, I think I said in one of these talks that one fundamental aspect of quantum physics is that it is probabilistic in nature. That is, when you make a quantum measurement, there is a probability that you will find one result or a probability to find another result, and you never know in advance. Some people don't like this feature, and they try to avoid it by saying that when you make a measurement, you will find all the possible results, except for the fact that there is one that you see, and the other correspond to evolution in parallel universes that you will never be able to reach. So each time a measurement is performed, the universe is branching into different branches, and we live in a world where all kinds of things may have happened, but you see only one history. So there are multiple histories. There are, for example, a history in which Napoleon won at Waterloo, and many things happened. Maybe, I don't know, maybe some universe in which Trump was not elected president of the United States. And so this is a theory of multiverse theory of quantum physics, which I don't like personally because it's really mind-boggling what happened. Now, there's another aspect, which is there is no reason why the Big Bang created only one universe. So there are theories saying that there are many parallel universes which have been created by different aspects of the Big Bang, and these universes are parallel and cannot communicate with each other. But as long as you don't have any communication, I don't think it's science, it's just speculation, because science has to rely on experimental verification, either direct or indirect. So I don't know. There are some theories which imply that you may have many parallel universes, but really I don't know about that.
What is space? You said space consists of dark matter, dark energy, and other matters, but we still say space is vacuum. Why?
Okay, the vacuum is a very, in quantum physics, the vacuum is a rather subtle object. Okay, in classical physics, the vacuum is the fact that you have nothing. But according to quantum physics, you can have fluctuations. For instance, you can have in vacuum the creation of pairs of particles and antiparticles. So you can have also a particle which appears, or photons which are created and disappear. And all these phenomena which occur in vacuum give some properties to the vacuum which can be observed experimentally. For instance, if you take an atom and look at the energy levels of the atom, quantum physics tells you clearly, for example, for hydrogen atom, that the energy level should have this and that value. But there is a small correction to the position of the energy levels, which is due to the fact that between the electron and the proton, you have a vacuum, and that this vacuum can be polarized. It can have particles which are created in this vacuum and disappear. And this has a very small effect, which slightly changes the position of the energy levels. This is called the lamp shift, and it has been observed experimentally. So there are evidences that the vacuum is a system in which it is a place where things can happen virtually. That is, particles can happen and disappear all the time. This is true for the electromagnetic field, but the other fields also fill the vacuum. You have Higgs bosons, for instance, which are everywhere in the vacuum. But in order to detect really these particles, you cannot extract them from the vacuum. They change the properties, they affect the properties of the vacuum, but to observe the particles, you need to produce energy, and so you need accelerators and all kinds of technologies. But the vacuum has this kind of property, and now you might have properties of the vacuum which are related to the dark energy and the dark matter, but this is speculative.
Okay, thank you, sir. The last question of the session. Does gravity affect the light? If so, then why can't light pass through a black hole?
Why?
Does gravity affect light?
Yes.
If so, then why can't light pass through a black hole?
Deep black hole, okay. Okay. Can it pass through? Okay, gravity affects light, yes. In fact, the light is propagating in space, and if the shape of space is modified by heavy masses, the light follows the curvature of space, and the light is curved around heavy masses. In fact, this was the first evidence of validity of general relativity. Eddington in 1919 observed during the solar eclipse, he observed the position of stars which were just behind the sun, and he saw that the position of the star was slightly different from what it should have been without the sun blocking the way. So the light was slightly deflected by the sun, exactly by the quantities that general relativity predicted. So light is affected. And now the question is, what happens in the vicinity of black holes? Okay, if you take the mass of the Earth, and if you want a particle to escape of the attraction of the Earth, it has to have what we call the escape velocity, which is a velocity given to rockets which are launched to the moon or to go faster to a larger space. So, and suppose that you increase the mass of the Earth and the density of the Earth by a large amount, the escape velocity will increase, of course. And there is a point where the mass and the density will be so large that the escape velocity will become the velocity of light. At this point, even light could not escape. And this point is exactly the density that you need to have a black hole. So in fact, one way to understand the black hole is to have, it's a singularity of space which is so big that even light at the velocity of light cannot escape the gravitational effect. And that's my simple, intuitive description of what a black hole is.
Okay, thank you, sir. Here we arrive at the end of this interactive session.